English because our guest is coming from Brazil, and the talk will be held in English. And the thing is that I contacted a dear friend and former colleague, Christian Rummel, asking him whether he is willing to give a talk here in the neuroscience seminar. And he said to me, well, I'm doing other things now, but somehow I'm connected with a subject of universal scaling laws of mammalian brains. And I told him, well, that's great. That is really a very good subject for this seminar here in the Complex Systems Center. So please give the talk. And then he told, well, but I'm just taking advantage from the work of other people. And he told me that the heat of this project is Bruno Mota. And he gave me the contact, so I wrote to Bruno, and he was willing to give a talk today. So Bruno is the head of the experimental mathematics and theoretical biolab at the Physics Institute at the Federal University of Rio de Janeiro. And please feel free to interrupt, but we have to use the micro. If you have any kind of question or suggestion or comment, that will be very invited and would be very nice if you would have a vivid discussion as usual. And Bruno, thank you very much for being with us, for giving this interesting talk. And now everything is yours.
Thank you very much. It's a pleasure to be here, even if just virtually. I apologize for giving this talk in English. My Spanish is ear-bleedingly horrible. So I'm sorry I could not speak in your language, but what I want to do is to give an overview of this line of research, which I've been working on for about a decade now, and has been very fruitful at the intersection of physics and neuroscience. And I want to give it from the perspective of a physicist, because in this clash of cultures, sometimes things that we find interesting and things that the neuroscientists find interesting are not always the same. And I saw the enthusiasm with which Marcus mentioned the concept of universal law. So I think I'm being closer to you, this audience, if I give my own perspective. Now, the talk about today is about the shape of the cortex, the largest part of our brain. And I'm going to structure this as a series of questions because as a research program advances, the initial question that you have turns out not to be the most fundamental one, the most interesting one. So you ask deeper questions and deeper questions. And in my experience, asking the right question is a much harder endeavor, a much more significant endeavor than actually answering the question. Because once you ask the question correctly, then the answer comes more naturally. Then less well-posed question. So in the end, what I'm trying to propose here, that's something variables and really an entire framework through which you can express all the shapes such as this thing which I call a sync is a more useful, more insightful, more interesting way of describing a brain than simply giving you the positions of various folds as done today. And I want to convince you that this new syntax is a potentially very powerful tool that enables us to understand cortices as abstract objects in a much deeper and possibly more relevant way. So let's start with the cortex. What is the cerebral cortex? Cerebral cortex is this folded structure composed of this thin layer of gray matter enveloping a core of white matter to which connections are made. And it's a structure that's exclusive to mammals. All mammals have it. No mammal have it. And it comes in a wide variety of shapes and sizes. Some are very big, some are very small, some are highly folded, such as ours, some are more highly folded than ours, some are very smooth. And it seems at first glance that it's not a particularly good candidate for seeking universal laws. Everything seems very specific to a specific species. Everything seems very continuous. But as we're going to see, these enormous numbers of apparent degrees of freedom can be boiled to an effective representation. Yes, yes. You cannot hear me.
Sometimes we are losing contact eventually. So maybe it helps if you're switching off your camera and
okay,
in order to have the. Thanks.
Okay, do interrupt me if I ever break up again. So I'll just repeat what I just said. These objects, they seem very unique and very contingent, so they seem to be a poor candidate for an attempt at generating universal laws, as we normally try to do in theoretical physics. However, as we're going to see, there's apparently enormous numbers of degrees of freedom with which one needs to describe these objects can be boiled down to a much lower dimensional representation that effectively captures most of the variance across these enormously different shapes. And that's what I'm going to be presenting today. So, yeah, shapes and sizes, and that's something I want to focus now because at a later point, we're going to see how we can express size and shape in an orthogonal manner using a new set of variables. So what do I mean by cortical shape exactly? We have to define this before we go on. And there are many ways of doing this, but my favorite way is thinking that since we're talking about a folded thing, a folded thin structure, areas are the natural way of measuring size, not volumes. And surfaces are the natural objects with which we are going to be working. So I abstract these shapes as three nested surfaces. This is a cetacean brain, a whale brain, because I want to be non-usual. And you have three contours here corresponding to slices of the surfaces. The inner surface is the white matter, gray matter boundary. That's where you connect the layer where the neuronal soma are to the layer where the long-range axons are connecting these neurons. Enveloping that surface, you have the PO or total surface. That's the uppermost part of the gray matter. It delineates all the boundaries of the cerebral cortex. And enveloping all that, we have what we call an exposed area. We can think of that as a version of the convex hull or some other surface that coincides with the PIO surface on the gyral outer surfaces, but do not go into each sulci in the interior. So it's a sort of shrink-wrapped envelope that envelops the surface. And these three surfaces, they are nested with each other. They cannot intersect one another. They cannot intersect themselves. That's going to be very important later on. So given this abstraction, we can start with our first question. How does the cortex fold? Can we provide a mechanicist model that generates folding in a way that's testably comparable to that of actual cortices? And we have proposed that this cortex, it crumples. It crumples in such a way that can be comparable to a paper ball. The idea is that if you take a series of paper sheets of the same aspect ratio and decreasing size, we can call this A5, A4, A6, A7 sheets of paper. We crumple them all. You're going to obtain a family of paper balls. And this family of paper balls, in some way, can be described by variables that also describe the cortical folding. And how is that so? Well, if you think of these paper balls, we can think of them as existing in a three-dimensional space. Because each sheet of paper has two intrinsic characteristics that do not depend on how they are situated in space. One is the total area of the sheet, and the other is the thickness of the sheet. And once we generate a paper ball, we generate a third extrinsic measure of the size of these objects, which is the area of the ball, the external area of the ball. And using these various three quantities, we can then see if we can derive some scaling law relating them so that this three-dimensional space is not it's not populated by paper balls in a homogeneous fashion, but rather we populate a submanifold within this three-dimensional space. And these three variables, they carry very distinct meanings. We have two measures of size, one intrinsic and one extrinsic, the total area and the exposed area. This carry naturally to the cortex using those surfaces I described before. And then we have a measure of the typical size of the folds, the thickness of either the cortex or the paper ball. Thinner cortices, presumably, will have smaller folds. Thicker cortices will have bigger folds. So given that we have three variables that naturally describe these folded structures, then we need some microscopic mechanics that will tell you how you can obtain an equilibrium configuration. And I won't go into much detail about this. First, because that's an entire world in itself, this model. And second, because most of what I'm going to say afterwards do not depend on this model being exactly correct. This model is going to generate a scaling law that's going to be empirically correct to have very high precision. And the existence of this empirical law is all we need to then derive this new morphological syntax. But the bottom line is this: we can think of the ensemble of all potential folded shapes, and we can associate this ensemble to two things. One is some effective energy associated with the dynamics of how this object grows and shrinks. And this energy is associated with the actions in white matter and the tendency to contract unless the longitudinal forces apply to them, at which point they start to stretching. And the second aspect is an entropy. Essentially, we can calculate how many microscopic states, how many folded shapes exist for one macroscopic state of a ball or a brain of a certain exposed area. This measure is an entropic measure, and it's dominated by self-avoidance in the sense that the more compact I try to make the ball, the more the surface of this sheet it starts to impact itself. And since it cannot interpenetrate, it's self-avoiding, it constrains the number of microscopic states possible for a given volume. So once we have these two components, we can define a free energy. A free energy corresponds to a measure that, when minimized, gives you the statistical equilibrium configuration. So we can generate a model, express those two quantities, the energy and the entropy, in terms using a approximation of the variables we defined before, the total area, the exposed area, and the thickness, and then we minimize this quantity. And what we obtain in the end is a scaling law relating the total area, the thickness, and exposed area, which can be expressed in two ways. Either the leftmost form, which segregates the entropic terms and the energy terms to the left-hand and right-hand sides, or as a relation between dimensionless variables where we define a scaling law between the total area and the exposed area, measured not in square meters, but in squares of the thickness. By this dimensionless parameter K, which is not defined by the theory, it's proportional to the effective temperature that goes into the free energy. And what we then predict is that this scaling law is going to be describing actual cortical shapes. So we actually have done these measurements. We measure a few dozen different mammalian species, and what you get, oh yeah, there's just one more thing. So we can think of this as akin to the idea that if you have a free energy F on the y-axis, and we define a quantity phi that's 0 for a completely smooth brain and going to 1 for an infinitely girified brain, we can see that depending on the size of the brain, the total area measuring multiples of the thickness square, the minimum of this free energy corresponds to either a smooth brain, which we call lissencephalic, or to a non-smooth brain, which we call girocephalic. So the idea is that both smooth and non-smooth brains can be encompassed by this theory, depending on where the minimum of the free energy is situated. And then when we compare this to actual data, each point here corresponds to a species, and each color corresponds to an order, from primates to cetacean, not cetacean here, primates, to rodents, to carnivores, to marsupials, and everything else in between. What we see is that we obtain, according to the expected relationship, a very nice fit. Not only we have a very precise fit of a power law, but we get an exponent that using these measures, which are somewhat crude, the measure of thickness is not perfect, we get very close exponent, 1.30 to the expected 1.25. This can be analyzed in many ways, but one that I'm going to just describe now and leave it for later is that we can define along this scaling law the point at which the cortex ceases to be folded when the exposed and total areas are the same. And this occurs when the scale of the fold, of the smallest folds, is compared with the scale of the entire cortex itself. And this happens when the area of this cortex is proportional to the thickness squared times this power of this dimensionless coefficient k. Now, another way of interpreting this is saying that this coefficient k is invariant across species. And we're going to see this later as a prototype for a new set of variables, but that's for later. Now, there's one exception to this rule, which is what happens if it includes cetaceans, dolphins, and whales. They're only fully aquatic mammals that exist. And we see that if you include them, they're like these dark blue points on the top here. They seem to be slightly elevated compared to the trend line for the terrestrial mammals. And if you look at them compared to their closest land relatives, the artiodactyls, you see that separately both orders seem to obey this universal law, but jointly they seem to have a gap. And these gaps correspond to a difference in the value of k. Now, the data here for the cetaceans is very old. It dates from the 60s when people didn't have computers and they had to use graduate students with acetate plates, essentially drawing on them on grids. It's very primitive, not to criticize people there because they didn't have any other tools, but that's not data we can completely rely on. So we have the indications that for cetaceans, this k coefficient is slightly elevated. We have some reason to believe that's so, because if you look at the derivation of the formula, we have a term that corresponds to the force per unit right section area of the axons that has the same dimension as the pressure. But we also have an actual pressure, the hydrostatic pressure under which the brain is submerged. And we know that this is approximately 1 atmosphere for land mammals, but it can vary enormously and be much higher for deep diving species. So this K coefficient is corrected by the pressure of the cerebrospinal fluid. So you would expect cetaceans, especially deep diving ones, to obey, to have an elevated K. Now, we hadn't started a project where we collected cetaceans, have the largest collection of cetacean brains in Latin America, really. And we scanned them in a very high resolution MRI machine. And then we reconstructed them using some machine learning algorithms. And these results I'm going to show you, they are 12 hours old. I just got them yesterday, so they're not really polished up or anything. But what we get is something like this. So we have the cetaceans on top and the terrestrial mammals on the bottom. And it seems that there is a genuine discrepancy in K, systematic discrepancy in K, probably related to the fact that cetaceans are deeper diving. So I won't say much more about this because this is very preliminary, but it seems that this old data is confirmed. Okay, so moving on. We then can analyze different sets, data sets for human MRIs. And what we have shown is that if you look at humans, adult humans of a certain age bracket, they also obey this universal law. They also have a slope of 1.25. The relationship seems to be obeyed very precisely. And that's true for all age brackets, for all data sets. However, if you compare different cohorts of different ages, we see that this coefficient k, which corresponds to the offset of this log-log plot, it decreases systematically over age. We see here, using this OASIS data set, that younger cortices tend to be higher on this plot, and as you age, they start to go lower. Now, this is for healthy brains, and that's true not only for the entire cortex, but for different lobes of the same cortex. However, if you look at patients with Alzheimer's disease, what we notice is that this K coefficient, therefore this offset, is always much lower. It's always systematically lower and doesn't seem to change over age. It's as if Alzheimer's disease is, morphological at least, is a premature aging of the cortex. So this new theory has led to a prediction that we'll verify experimentally in healthy brains, but also a potential way of generating biomarkers, morphological biomarkers for Alzheimer's disease and potentially other neuropathic conditions. So we do have universal law. It's true across species. It's true across human individuals, regardless of sex. And as I briefly mentioned, I want to go into detail, it's also true across different regions of the same brain. So it seems to be truly universal, but there's a one-fourth aspect of this law that we still need to verify. Is it true for the same brain over different length scales? And that's possibly the most significant relationship, because that will show that there's a fractal nature of this folding. So that's what we're going to focus on now, this four aspects. Is it true across length scales? But for that, we actually need to refine our questions. Because like we proposed that the cortex crumples, we have a model for that. We have a scaling law that can be empirically tested. However, there are other models, other theories that have been proposed, and there's some evidence for those theories as well, that the cortex, it warps like a piece of wood has been left in the sun, or it extrudes as neurons migrate outwards from the ventricular zone, or whatever else. And these can also generate folded shapes. So how can I compare these different models? That's a non-trivial question. And to answer that question, you have to think a bit deeper about what exactly we are measuring, because before we understand how the cortex attains this shape, we actually have to understand what the shape is. Mathematically, how can I express those shapes? And that leads us to a second question. What is the shape of the cortex, regardless of how it gets there? Now, there are many ways you can answer this question, and most of them are not particularly illuminating. We can just get one big cortex and express it in terms of these coarse grain variables, such as what's the volume, area, and thickness. Now, this works, but there's a lot of ambiguity in there, in the sense that many different shapes can have the same values for these variables. So this is a summary description that's not particularly informative. Alternatively, we can describe the surfaces by some triangulation, and we can describe individually each of these triangles, the areas, its orientations, where its edges meet, where its vertices meet. Now, that's a very detailed description with many, many, many degrees of freedom, but it's not very generalizable. If I just take the same brain and rotate it by 1 degree, all these numbers change, and there's not an obvious way of showing that they are the same brain, or that two brains are similar, or two brains are highly dissimilar, or one shapes the brain and one is not. So we need some sort of synthesis, something in between that enables us to retain the analytic properties of coarse grain variables and the descriptive power of the fine grain variables. And that's what we're going to be doing over the next half an hour or so. So let's go back to our question. What is the shape of the cortex? And let's give you a very simple, correct, but very vague answer. Well, some of these cortices are big, and some of them are small. Some of them are highly folded. The term for that is gyrocephalic. Some of them are smooth. The term for that is lysocephalic. So how we can capture this? If you compare the brains of, say, a manatee and a cow, we see that we have two social animals of roughly the same intelligence, and the manatee it has almost no folds in it, while the cow is highly folded. The Portuguese used to call the manatee the sea cow. That's why I like this comparison. So clearly, we need to capture size and shape, possibly in different variables. So to see how we can do that, I'm doing something very simple here. We're going to do something I call comparative rectangology. So imagine you go to an island and find these species of rectangles. You never see rectangles before, but you see that they come in various shapes. Some are bigger, some are smaller, but it's hard to compare because they come in different shapes. And you see that all of them can be characterized by two numbers, the height and the width. So each rectangle sits at one point in this parametric space. Now, some of these rectangles are special, we call them squares. The height and the length are the same. And we want to separate the expressions of area or of size and shape, so they can say these two rectangles are the same size, these two rectangles are the same shape. And the natural way of doing this is by expressing the areas and aspect ratios of these rectangles, the product of height and length, and the ratio between height and length. Now, by the magic of logarithms, we can see that if you express this in log space, then the area, the log of the area becomes the difference, or the sum of the logs of height and length. And the log of the aspect ratio is the difference between those quantities. So we can now think of area and aspect ratios as diagonal directions, as a literal unitary change. Going along the right direction, okay, I'm back. How much did you miss?
I think it was about maybe 1 minute.
Okay, so
More?
let's
2 minutes. Sadie said, sorry? Less than 1 minute.
okay, good. So just to recapitulate slightly. So if you just look at the log of these quantities, then the area is the sum. The log of the area is the sum of the logs of height and length. The log of the aspect ratio is a difference. So we can now express any point in here along these two new axes. One gives you how big the cortex is. One, this rectangle is. The other gives you how skinny or fat this rectangle is. So we can define directions of the same shape and the same size. Now, can we do the same for cortex? And the answer is yes. So if you look at universal law, remember there is one quantity that we say is empirically universal, the dimensionless quantity called K. If we simply isolate K in this relationship here, we can define this as a morphological variable. And if you take the log of this, you notice that this K is expressed as a product of power laws of our original variables. So you can think of K as a new direction in two-dimensional space, or log space. And this direction corresponds to shapes that do not shape, or corresponds to different quantity, different objects that are not sensitive to the actual size of this object. If I isometrically grow or shrink this object, it will retain the same K. So if you look at remember the paper balls, you can check to see that these paper balls connected by purple lines, they have essentially the same shape. They just isometrically scale up or down in a statistical way. The isometric scale up or down versions of the same shape. So we can think of in this two-dimensional space of log of total area, exposed area, and thickness as a direction that corresponds to moving from one paper ball to the next along these purple lines. And this corresponds to increasing all the area variables, the total area, exposed area, and the thickness squared by the same factor. So that's the direction, is a diagonal direction on this two-dimensional space. So we define this quantity as I. The log of I is simply the sum, or the I is simply the sum of the logs of these various fundamental areas. And since K is dimensionless, a change of I will not change it. So therefore, I and K are orthogonal to one another. And finally, we can just take the vector product of these two quantities and define a new variable, which call S. And for the same reason, this Sk, this variable is always also going to be dimensionless. So we have in the end three variables derived from the three variables we had before. This corresponds to a rotation of our basis. It's a unitary transformation. It's a new orthogonal basis where one quantity captures all the information about the size, that's I, And two other quantities capture all information about the shape. And they are orthogonal to one another. You can change size without affecting K and S. You can change shape without affecting I. So these new variables, in a way, more expressive, and as we're going to see, more statistically independent from one another than our original variables, and they are better way of characterizing cortical shape than the variables we started with.
Just one question is that are
Yes.
really peculiar is the relations which you're writing down there, S and I. How did you found these relationships? I mean, you're looking for scaling laws, and you're looking to try to characterize possible fractal nature of this structures. So how did you get these very strange?
Okay, we started one variable with scale, because we know that empirically, the universal law says essentially that the K quantity for different cortices is invariant. So we can start with that quantity as our initial variable, new variable. And in terms of this new quantity, we can say that all the cortices, they lie on this plane that is perpendicular to the K direction. So that's a dimension reduction there, right there and then. So that's our first variable. Now, we notice that this K is dimensionless. So if you just take the same cortex and shrink it or grow it isometrically, it's not going to affect in the K. So what's the difference between these shrunken or expanded cortices? And this corresponds to a change in the I direction, where you just multiply all the areas by the same factor. So this gives you the second variable, I, that's perpendicular to K. And finally, we need a third variable that's perpendicular to both I and K. And since I captures all the information about the size, this S variable is also dimensionless. So it's a different aspects of shape. So now we have three variables, one for size, two for shape. And of these two shape variables, one of them is invariant, and the second one varies across different species. So we can call this varying shape parameter or variable as a measure of morphological complexity. A less complex shape, a smooth shape, has a small s. Highly complex, highly convoluted shape has a large s. So that's how it come about, these three new variables. Okay? So
thanks.
Okay, so just to finish the discussion about these new variables, one thing that we can ask is, okay, how statistically independent are they? Because we know that the original variables that we had, the total area, the exposed area, the thickness, they are not statistically independent. They are very tightly correlated by this universal law. So you cannot make a univariate measure and say that captures all the information about that variable without taking account the other ones. But if you look at these new variables, that remember, they were not derived to be statistically independent. They were derived to make sense of shape and size independently. We see that they turn out to be highly statistically independent. If you take the data sets for both humans and primates, and if you do a PCA, a principal component analysis, to see what the independent components are, we get these black axes. They almost exactly coincide with the axes defined by these three new variables. So not only these new variables make sense in terms of shape and size, but they also separate our information in statistically independent quantities. And then we can do something more. We can look at different neuropathic conditions, in this case, temporal lobe epilepsy, Alzheimer's, and aging, and see how they compare across these two sets of variables. Remember, this is exactly the same data. So we're just expressing this data in two sets of equivalent variables. And if you look at the original variables, what you see is that all the three variables change in all cases, but the most significant changes in all cases is that for both aging, Alzheimer's, and temporal lobe epilepsy, the thickness is decreasing. Okay. Now, it would seem then that these all these conditions are doing pretty much the same thing to the shape of the cortex. But if you look at the new variables, something much more interesting happens. We see that in this case, the most significant difference between them is that for Alzheimer's and aging, the K coefficient is decreasing. It's as if in terms of the original model, the density of axons in white matter is decreasing because they are dying off. While in temporal lobe epilepsy, this K coefficient is increasing, which means that they have more axons that would normally otherwise have in a healthy cortex. And that's also compatible with what we know about epilepsy, which it can be generated by deficient or insufficient pruning of connections in the developing brain. So you see that these new variables, they are not only more expressive in terms of capturing shape and size, but they can better segregate between different neuropathic conditions and potentially generate better biomarkers.
May I interrupt again?
Sure.
Sorry. So if I understand correctly, the S variable somehow is a measure for the degree of complexity according to some criteria. Did I understand that correctly?
Yes, you did.
So isn't it surprising that in all three pathologies which you're considering here, that the complexity of the cortex increases?
Yes,
I would have intuitively, I would have suggested it's quite the opposite round.
Okay, so that's a question we ask ourselves, and we don't have a complete answer for that, but I will ask you to notice two things. One is that in all three conditions, the I is decreasing. So in a way, it's as if the cortex is shrinking, okay? And as it shrinks, if you look at those brains, the sulci, they start to separate as well. So in a way, morphological complexity doesn't imply necessarily computational complexity or a better adaptability. It just shows that the shape is harder to describe. So in the end, we get a more complicated shape. Doesn't mean it's a better shape. That's not a complete answer, but that's our intuition so far. That's what's happening in all three cases. Remember? Just that in all three cases, the thickness is decreasing. So if you have something that's thinner, it's easier to fold. So I think that's related to how the morphological complexity is increasing in all three cases.
So looking to these three variables, it seems that you are able to distinguish very nicely the control group with the pathology.
Yes.
But if you're looking just to the thickness for itself or the exposed area, or how? Okay. Yeah, thanks.
Yeah. So we can distinguish in all cases almost as well the control from the
pathology. The thickness seems to distinguish it very nicely, even better than the.
Well, not better, but it does distinguish them. But what we see is that we cannot distinguish between the pathologies. So if you want to say, okay, what's the characteristic of an Alzheimer brain compared to an epileptic brain? And the original variables, they cannot tell them apart. I mean, no, they're highly different because the microscopically, what's happening to the axons is very different. But the new variables are perfectly able to differentiate between them. Okay.
Okay.
Okay. So, okay. We are still working on these biomarkers, but before I get back to biomarkers, I want to go over these analyses over different scales because that actually improves these measures in ways that I hope are going to become clear sooner. So are there other questions? Okay, so moving on.
The chat, if I see it correctly.
Okay, let's
maybe have a look. Maybe have a look on that.
Oh yeah, can you read out any questions that are in the chat for me because I have to get out of the shared screen to access that.
Oscar, may you visualize the chat? Seems that there's a question. I will read it.
Yeah, please.
Just a second. No, it was just the answer that we missed you 1 or 2 minutes.
Okay,
no
good.
question.
Okay. Anyway,
okay.
Please feel free to ask questions at any point. I think it's better than leave them to the end. So we started from the question, how does the cortex fold? Then we saw that first we need to answer what is the shape of the cortex. But if you think in terms of statistical physics, we're not interested in one cortex. We're interested in a family of shapes that corresponds to cortices. So if you think of the full ensemble of all potential folded shapes, we can ask ourselves which among those shapes can correspond to an actual biological cortex. So that's what we're going to do. And we're going to answer that question essentially by melting the brains. So what are the shapes of cortices? What is the set of shapes that corresponds to cortices? So just remember, these are really diverse set of forms. And these forms, however, are only a small subsample of all potential folded shapes. So among all potential girified structures which may correspond to cortices. And this is directly related to the question, are cortices fractal? Because if they are fractal, it means that saying that something is fractal, is approximately fractal, is a powerful constraint on the possible shapes that it can take, because it says that the small folds must be similar to the big folds. So you don't have the freedom to have one type of fold for small folds, one type for medium folds, one type for big folds. So why would you suspect that the cortex is fractal? Well, because if you look at the relationship, the inverse relationship that have found empirically to be valid across species and individuals, we see that it's a relationship very similar to what we get in scaling laws for fractal shapes, because it relates how an intrinsic measure of size relates to an extrinsic measure of size given the size of your fundamental tile. If I try to delineate a literal using a certain size of ruler, I'm going to get a certain value for the perimeter of this literal, and that's going to be dependent through a power law, if the literal is fractal, to the size of the ruler. So if you look at, say, the Britain's coastline, we see that if you just trace it over bigger or medium or smaller rulers, we get different size of the coastline. And that's such a significant result that asking ourselves what's the size of Britain's coastline is a far less significant a question than ask how the size of this coastline changes with the shape of the ruler. And we see that there's a power law relationship that is steeper for a more convoluted coastlines such as Norway's than for smoother coastlines such as South Africa's or Australia's. Now, if you think of this in a more mathematical way, we see that if you have something like a cork curve, and it has various approximations of this cork curve, that we can also express an intrinsic measure of this of the length of these approximates in terms of going every indentation, and an extrinsic measure of this the same length, which is the distance between initial and endpoints. And we see that there's a parallel relationship between these two quantities on one hand and the size of the smaller structure or the size of the ruler at each iteration on the other. And that's true regardless of whether you keep the extrinsic size constant and change the size of the ruler, or if you keep the size of the ruler constant and change the extrinsic shape. In all cases, we have a power law, and the exponent of this power law is going to be, in this case, the fractal dimension, or in general, the ratio between fractal dimension and the topological dimension of these objects. So for the cork curve, we can very easily derive this quantity as being the ratio between log 4 and log 3, 1.26. Now, if you look at the cortex, you have a very similar relationship. So if this relationship is results from a fractal scaling, so these exponents should be the fractal dimension divided by 2. So if this exponent is 1.25, as predicted by the theory and verified empirically, then you should expect a fractal dimension of 2.5. And in fact, other groups have measured this and obtained a very similar value of 2.49. Now,
but I have another question. Sorry for interrupting again.
No, go on.
I mean, this scaling law which you're showing is really impressive. I mean, all the experimental dots are following very nicely the theoretical curve. But is there any intuitive argument why it is convenient for the brain having a fractal topology? Is there some intuitive?
So that's a very long discussion, but people have often assumed that the brain is girified because that's adaptive. That's something that evolution chooses because it, say, minimizes wire length or something else. Now, what I'm proposing here and what I believe is that given the area of the cortex, the total area, and given the thickness, the folding of the cortex is a purely mechanical process, a purely statistical mechanical process. Evolution doesn't have a choice of how the brain is going to fold, given the area and the thickness. So I'm saying here is that actually that's not. I'm restricting the degrees of freedom that evolution has. It doesn't get to choose whether a brain is highly folded or not. Given that it decided to create a cortex that has a certain thickness and area. So intuitively, I'm saying that's not something that optimizes some evolutionary goal. It's simply a physical process. And what evolution can do is change the thickness and change the area through various means so they can generate something that has, say, longer or shorter wiring lengths. But that's it. That sometimes offends the biologists, but I like that some things have physical causes rather than evolutionary ones.
So you think that if you are if one could optimize the intellectual abilities, that might change the fractal structure? I mean,
no,
you're telling us that it's just a physical process why it has it came to this structure. So, but it's not an evolution. Sorry.
Yeah, I think the opposite. I think that if you optimize intelligence, you might do a number of things. You can, say, increase the number of neurons. You can make the cortex bigger, but given those choices, how the cortex is going to fold is going to follow the exact same universal law. So that's not something that evolution can change in healthy brains.
Right.
I mean, obviously, this doesn't mean that evolution cannot optimize intelligence through other means. It's just that this particular aspect is frozen by the physics of it. So, I mean, we still haven't proven that the cortex is fractal. We just showed that it follows the scaling law that you would expect to see if the cortex was fractal. And other people have then shown that by doing a box counting procedure on the cortex, that they obtain a fractal dimension that's actually very close to what we predicted. So we predicted 2.5, they actually found 2.49. Now, what we need to do now is then to do a similar procedure as this, but in a way that does not destroy the intrinsic self-avoidance nature, a mutually avoided nature of the cortical surfaces. And I won't go into detail about how we did this, but we managed to create a procedure that essentially starts from a cortical surface, say between white and gray matter, does a coarse graining on the voxels, and then use the surface we had before to resegment these new voxels, and then apply the original algorithm to generate a new surface. So we have a series of surfaces that are self and mutually avoiding. And what we get is, as we decrease or increase the size of the smallest structure, as we erase the smallest sulci and gyri, and as we do that at each stage, we obtain the image for the cortex at that stage, and we put them sequentially in a movie. That's what we get. On the left-hand side, we have the gray matter. On the right-hand side, we have white matter. And this is the cortex melting. That's a human cortex that starts highly girified and proportionally very thin. And as time passes, as we delete the structures smaller than a certain threshold that will then increase over time, the cortex becomes smoother and proportionally thicker, like this. And we can do the same with other species. For technical reasons, we have only done so for primate species so far. We've done that for 11 primate species. So this is what happens to macaque. And just to make sure that we are not obtaining something that is intrinsic to the method rather to the object of study, we did the same thing for a walnut and for bell pepper and for a number of other things. And what we see is, I think, very striking. So you remember the scaling law relating the total area and thickness to the exposed area. Now we start from different primate cortices, which they start of each of these color lines. And as we melt them, as we go along those movies, we plot the frames of that movie with the same color. And what we see is that all these lines not only have similar slopes as seen here, close to the predicted 1.25, but also they all overlap. And that I think is very striking, because what this is saying is that the cortex is indeed fractal, that if you coarse-grain a cortex over a certain threshold, it still retains the same shape as it had before, so that the bigger folds, they have the same scaling laws as smaller folds. But not only, because when you say something is fractal, what we're really saying is that something approximates a fractal. There are no fractals in nature. What they have is something that approximates a fractal over a range of length scales. Okay? There's a largest scale, which corresponds to the size of the objects, and the smallest scale corresponds to the size of the smallest structure. Now, what we're saying here is that all the cortices we have analyzed, they approximate the same universal archetypical fractal. And that's such a significant result, because then what's the difference between the various cortices? Why is my cortex different from that of a giraffe or a platypus or a chipmunk? And the answer is that the cortex differ in the range of scales for which the approximation is valid. For a highly gentrified cortex, this range is broad. For a less gentrified cortex, this range is slightly narrower. And for a lissencephalic cortex, this range collapses to a point. So that's what we're going to say, what is the shape of the cortex? They are approximations of the same fractal shape, and the validity of the approximation in terms of the largest and smallest scale for which it's valid is what differentiates one cortex from the other. We can do the same thing over many other morphological variables, and we see that all of them, for each cortex, corresponds to a range of values that is some power of what we call the gentrification index, the ratio between total area and exposed area. And that's the difference. That's what differentiates me from a giraffe, this range. Now, this gives you something I think very cool, because it allows us to abstract a cortex, not as a high number of triangles in space, not as a few global variables, but rather as a trajectory in this two-dimensional space. So each different cortex corresponds to a different trajectory. And this is a description that at the same time highly analytic, but also fine-grained. We can think of this trajectory both in the original variables and in the new variables, they say essentially the same thing, in terms of a fundamental scale lambda, the size of the smaller structure. So they have now three functions of lambda. And that is our abstraction of cortical shape. And that's what we're going to get in the end. So just to sum it up, I still have, there's something I want to go very briefly in the end of this, but that's like something we're currently working on. But I want to summarize these results because these close very nicely, I think, this research program that I started a decade ago. See? So to answer the question, what is the shape of the cerebral cortex? Well, we have developed a simple syntax to express that shape. And we show through that syntax that this shape is a fractal down to a cutoff scale that's proportional to gray matter thickness. This scale is valid across species, individual cortical regions, and scales, length scales, so that's universal. And in a way, fractality recapitulates phylogeny. Different species, they differ mainly on how along this hierarchy of folding process the cortex is. This scale is specific to cerebral cortex. We haven't shown this here, but it's not valid for walnuts or bell peppers or whatnot. And this provides a very stringent test for any potential model for cortical folding. It must produce this scaling under coarse grain. In the end, we have shown that all cortices are the same. All cortices are approximately the same. The range of approximations where this is valid is what differentiates one from the other. So that concludes, say, the research I have done so far. The paper with the analysis, the multi-scale analysis where I show this fractality has been published relatively recently, last year in eLife, and I welcome you all to read critically. But I just want to go very briefly about what's next. So to go to what's next, usually good. It's usually useful to revisit what I have done before, because I have described the cortex as three nested surfaces. But that's not a sufficient description. The surfaces have properties that we have to impose in some sense, and previously I only posed them after the fact. These surfaces are closed or can be closed. They are simply connected, they are homeomorphic to a sphere, and they're self and mutually avoided. They cannot cross themselves, they cannot cross each other. That's by definition. And these properties, they are not implicit in the description I had before. So currently what we have is a description we essentially map either a plane or a sphere into two-dimensional space, and then censure this new shape to avoid crossing itself. But what if we express that surface not as a mapping of a sphere into three-dimensional space, but rather as the equipotential of some scalar field defining over the entire volume? So this is an analogy. If you imagine that you want to describe the region between white and gray matter, we can think of the white-gray matter boundary as a region that's hot. We define it as a temperature of 100, whatever units you want. And then the biosurface, the outer layer of the gray matter, we define it as cold. Now, if you have a temperature distribution in between, we can think of a process where heat is transferred from the hot boundary to the cold boundary. Define this as a boundary condition. So it's always hot and cold at the white-gray matter boundary and the pure surface. And we're going to have heat flow. And we can ask ourselves, what happens if we leave this long enough so that we have stationary heat flow? Well, it means that at each point, the amount of energy or heat that comes in is exactly the amount of heat that comes out. And on that, not equilibrium, but stationary distribution, we can define equipotentials of different temperatures, 25, 50, 75. And by looking at the gradient of this now divergence-less field, we can define these curvilinear these curves that smoothly go globally from one surface to the other. By measuring the length of these curves, we can have a measure that's a bit more precise of the thickness of these objects. Now, this can be done in a very mathematically well-defined way by essentially defining this scalar field inside these two boundaries and solving Laplace's equation, where the Laplacian inside the boundaries is zero. This is univocal, this is well-behaved, this is probably the most well-behaved equation there is, and allows us to do a number of things. I want to go very briefly over what this means. One thing that we can do is, since we can flow one surface to the other, we can define the quantities that we're interested, such as the total area exposed area thickness, or K, S, and I, any variables that we want, and we can localize them to specific vertexes. We do this by using the Gauss-Bonnet theorem to essentially calculate what these quantities would be in a certain patch of the surface if we have the entire cortex having the same properties of the same patch, the same average curvature, the same average thickness, or whatnot. And we can do this and obtain for each point in the cortex a value for these quantities. So now we have a map of K, S, I, thickness, area, volume, whatever, localized over various points. That allows us, for instance, to investigate conditions that are localized, such as temporal lobe epilepsy. Another thing we can do is to derive a new and more effective way of melting that does not necessitate going back and forth between a surface description and a volumetric description. And I don't think I have time to go into this into any detail, but if you think of a temperature distribution within these two boundaries, it's possible to define the heat equation in terms of independent modes of heat decay. Essentially, you solve Helmholtz equation, and each eigenvalue of the Helmholtz equation gives you one of these spatial modes, and the associated eigenvalue gives the rate of decay for this mode as time evolves. And the distribution you had initially, the solution of Laplace equation, corresponds to the mode where this eigenvalue is zero, and therefore it does not decay. So all the other modes decay, leaving us in the end with the stationary one. So what we can do is think of these various modes as describing different ways, different distributions of temperature as they evolve through time. And we see that the higher the eigenvalue for the mode, the faster it decays. And you can think of this as analogous to what we see when we try to melt something, a surface, and we delete the smallest folds before delete the big folds. So what we can do is something like this. We can define the boundaries between white and gray matter and define an initial distribution within those two that corresponds to the actual verification that they get. And as we evolve this through time, as we evolve to different spatial scales, the sulci and gyri that start push out and become smoother and smoother. And in the end, we obtain a series of shapes that interpolate between the original cortical shape and the lissencephalic shape, given a time scale that we can immediately convert to a length scale, and therefore we can obtain a new way of melting that is much more reproducible and much more well posed than we have done before. That's an active research. I don't have any final results to show you, but that's something I hope to finalize this semester. And finally, that's the last application. We can do something called call registry, because it's possible to decompose these shapes into eigenmodes. And if you think of this in three-dimensional, the fundamental eigenmode corresponds to a zero eigenvalue. It gives you the temperature between the hot surface and the cold surface, the white matter, gray matter boundary, and the pile surface. And each point in between gives you a generalized measure of thickness. So it gives you how deep you are along this cortex. And if you look at it further, the three next eigenmodes, they correspond to what we get in a sphere, a dipolar modes. They essentially give you three directions that say that three temperature fields that change in three different directions that roughly corresponds to the three axes of our brain. So it's caudal rostral from like this, it's medial lateral going like this, and it's ventral dorsal going like this. So if we take the temperature of each of these modes for each point in the cortex, it gives you a three-dimensional set of coordinates for this point. So what this does in the end is to map each cortex in all its enormous variety to a point into a hollow sphere. The inner surface is the white matter boundary, the outer surface is the power boundary, and I can take a giraffe brain or a human brain or an Alzheimer brain, a healthy brain, and map all of them to the same point or to the same space to see how they are distributed differently. And this, what you call spectral embedding for the entire cortex, is something we hope to do in the very near future. So I'll finish here. The lesson thing then being that if you abstract things in a way that answer more fundamental questions, things that seem very complicated turns out to be much simpler, and that things that are described by a high number of degrees of freedom can be effectively described by a much lower number of these if you can manage to find what the invariants are in this system. So I'll finish here. I'll give you a warning that theoretical physicists working on neuroscience can tend to oversimplify things. And then thank you for your patience and open the floor for questions.
So thank you very much.
Thank you.
Thank you very much for this very interesting talk and presenting this interesting results. So is there any question here in the audience or people which are connected via the internet? If you have any kind of comment or question, that would be now to express it. Well, I have a question. Maybe you know there's a certain set of people like Dietmar Plenz, John Bex, and Dante Chialvo. They are following the hypothesis that the brain is operating close to a critical point of a second order phase transition, and they try to collect evidence for that, looking for scaling laws, which they found actually. with different kind of measures and so on. So you are presenting a scaling laws here, and the experimental data is following very, very nicely the curve. Is there any relation to this hypothesis of the critical brain, or operating close to phases in this apparent fractal structure of the cortex? Is there any kind of relation to this?
It may be. It's actually hard to ascertain because it makes relating to very different levels of cortex. One is the morphological level, and the other is the action level, how the brain actual functions. So most of these analyses of critical points, they use EEG and look at the activities of the brain in the cortex. So to answer your question, I don't know. I'd love to find out. Now, there's some methods.
They're also using fMRI or implanted electrodes. So there are different kind of measurements they're using.
Yes, but they're always activity. It's always activity. So the fundamental intuition is the Pierre Bach's SandPile model, right? So we are at a self-organized critical point. Now, there's some really interesting work being done in Brazil, not by my group, but a group in Pernambuco, which I'm starting to collaborate, where they do something called Bialec's effective renormalization, where they look at not the shape, but the activity at different scales. And they think convincingly that they've shown that this activity in healthy brains, they are situated near the phase transition. Now, how does that relate to the shape? Now, clearly the shape constrains the activity. So it's possible that having a fractal shape enables scale-free activity to occur if you look at, say, the length of the various connections. Now, this is very vague, and it's vague because I cannot make it more precise, but that's something I want to investigate in the future in collaboration with those people. But if you're interested in self-organized criticality in the brain, they are the right people to ask. In fact, that's some people actually might invite to give a talk there because they're really doing interesting work. They're actually looking for this in EEG activity.
Thank you very much. Is there any kind of comment or question here in the audience? Well, if not, thank you very much. I was really, I think it's amazing your work, and I'm really interested. I would appreciate if you could send me this eLife paper. And if anybody here is interested, I could provide this work also.
Okay,
so if you could send me this paper, that would be...
I can put it,
Sorry?
I can put... before you close the room, I'll email that as well, but I can also post that on the comments so that people here that are interested in the eLife paper can have a look.
Perfect.
Just a second.
Thank you.
It. Okay.
There's another question.
I don't know because it's such a weird topic, but it took a year between submission and acceptance. So it has been going back and forth for over a year. Anyway, I just pasted the paper here.
Okay, thank you, Bruno. I have a question. Do you think that this is applying only for the cerebral cortex? Do you think that that it can be applied to other brain structures?
That's an excellent question. So the thing about the cortex is that it exists only in mammals. In, say, birds, the equivalent structure is the neopallium. It's not folded at all, and it doesn't have these layers of white and gray matter. However, there is a structure present in every vertebrate that's folded in every vertebrate, and that's the cerebellum. Now, the cerebellum is really cool because it is a much simpler microscopically than the cortex. It has just one type of circuit that's repeated systematically. And it also folded, except in some really weird electric fishes, it's folded in just one dimension. So instead of folding like a crumpled paper ball, it's folded like a sheet that has like these waves. Okay? So you can ask, if the folding in the cerebellum also obeys the universal law. And there's another paper that we published last year where we show that in a way it does not. Because if you generalize the universal law to the, say, instead of describing a two-dimensional sheet in two-dimensional space, you describe a one-dimensional perimeter in two-dimensional space, the exponent changes from 1.25 to 1.5. Now, if you compare different cerebellum, and you look at the scaling law, you get actually very precise scaling law, but an exponent of 1.8. So it doesn't seem to be obeying that. However, if you then subdivide this cerebellum into different lobes, like you do in a broccoli, you just take the bigger branching and then split it in two, and then the smaller branching split it in two, you see that as you go deeper and deeper in the cerebellum for smaller and smaller sub-branches, the exponent converges to 1.5 very precisely. Also, that's something that I'm doing with a master student right now. If you simulate, not a cerebellum, but a two-dimensional object that has two layers, that has an energy and an entropy that's the same as we have in our model, and you look at the scaling of this object as it achieves equilibrium, you also get an exponent of 1.5. So the end result, in my view, is this. There are other mechanisms in the cerebellum that define its deification other than this universal mechanism. But this mechanism is present and it's more prevalent in the smallest fold. And this mechanism is sufficient to generate the scaling that would predict by the theory, at least in simulations. So I think that's currently what I'll state. There's another set of objects that are actually, that's one of my labs called experimental mathematics, which is actual paper balls. Now, paper balls are very easy to generate. They don't need ethical approval, and they're very cheap. So I'm actually trying to put together some form of imaging of the inside of the paper ball so I can better characterize the scaling laws within the paper ball. And in fact, I know that some of the most preliminary work on the fractality of paper balls was actually done in Mexico in the 90s and early 2000s. So you probably have people in your university that are experts on paper balls. So those are the three classes of objects that I think can obey this universal law: cortices, cerebella, and paper balls.
Okay, thank you. Thank you.
Cheers.
Any other comment or question? So I have definitely to pay more attention to your papers. I will read them very carefully, and I hope we can stay in touch. Thank you very much for this very nice contribution. It was really interesting for me. Thanks a lot. Thanks a lot to all of you being here, paying attention, and to assist. And as usual, cuídense mucho y pórtense bien. Thanks a lot, Bruno.
Bye-bye. Bye-bye.